Have you ever received a package and just, tossed the box aside without a second thought?
Happens all the time.
Right. Those sturdy brown containers that bring everything from, like, your latest tech gadget to groceries right to your door.
Absolutely ubiquitous.
They seem so simple, so unassuming, almost invisible in their everyday use.
Yeah.
But what if I told you that beneath that plain exterior lies this fascinating world of intricate engineering, clever design, and surprising material science?
It's really quite something when you dig into it.
So today on The Deep Dive, our mission is to uncover the hidden genius inside the corrugated fiberboard, or CFB box. We're going to trace its journey from, well, a tree in the forest, all the way to the precise measurements that make it such an unsung hero of modern logistics using the great research you've shared.
Looking forward to it.
Get ready to have your mind well unpacked.
It truly is a remarkable story, isn't it? Something so common, so easily overlooked, is actually a masterclass in applying material science and design principles to what looks like a simple problem.
Which is just getting stuff from A to B safely.
Exactly. How to protect and transport goods efficiently. It's a testament to the complexity hidden in plain sight.
Okay, let's unpack this, literally. To begin, what is a corrugated fiberboard box at its most fundamental level? What are its building blocks?
Right. So at its heart, a CFB box is crafted from cellulose fibers, primarily from wood.
Yeah.
These fibers are first pulped and then meticulously formed into sheets. Now, when we talk about fiberboards generally, there are really two main categories.
And those are?
You have what we call solid fiberboards. Think of these as multiple layers or plies of paperboard laminated together, glued together, to create a single, dense sheet. They're flat, sturdy, usually between, say, 0.88 millimeters, almost 3 millimeters thick.
Like super heavy cardstock.
Yeah, something like that, but thicker and much more robust. And then there's corrugated fiberboard, which is our main focus.
Star of the show today.
Indeed. This is characterized by its distinctive, wavy middle layer, the fluting, which is sandwiched between flat sheets, typically strong craft paper. That wave is absolutely key.
It's incredible to think about that transformation.
Yeah.
From a living tree to that, wavy board. Our sources lay out a clear progression for this.
They do. It starts with the wood. That wood undergoes a pulping process, often the sulfate process, to become wood pulp.
Okay.
From this pulp, we produce craft paper. That's known for its strength, its long fibers.
Right.
And finally, that craft paper is skillfully converted into the familiar corrugated board. Understanding this whole journey helps us appreciate the properties of the final product.
Okay, here's where it gets really interesting. Once we get that basic journey, we need to zoom in on the components that make up the corrugated board itself. Our source materials point to three essential players.
That's right. We're talking about the liner. Those are the flat outer layers, the fluting medium, that's the wavy middle bit, and the adhesive that binds them all together.
Let's start with the liners. So the first thing you see, the outside of the box. What's their main job?
So the liners are typically made from craft papers, and they come in various thicknesses or grammages, GSM, usually between 80 and 225 GSM.
GSM, grams per square meter.
Exactly, grams per square meter. And the outermost liner usually has the maximum grammage, the highest weight.
Makes sense. It takes the most abuse.
Precisely. These liners are the box's first line of defense. They resist hazards like puncture, burst, abrasion, tearing.
Wow, a lot of jobs.
Oh, yeah. They also have to properly hold that wavy fluting medium in place, resist moisture either from inside or outside, depending on the product, and critically, they need to be good for printing, logos, shipping info, all that.
Right.
And for some uses, you might even find waterproof papers like bitumen, polycoated, or wax-coated liners.
So the liner is really the tough outer skin. Are there different kinds, different qualities?
Absolutely. And the quality really impacts the final dock strength. Generally, you see three main types. First, pure craft. That's virgin fiber, long, strong wood fibers. Top quality.
Got it.
Then there's jute or lint. This is often lower grade or uses waste pulp. Sometimes it's backed with pure craft to give it a bit more strength.
Hybrid approach?
Sort of. And finally, chipboard or straw board, which are typically made from recycled paper. The key thing here is that higher quality paper in your liners means a stronger, more protective box. It's a direct link.
That makes perfect sense.
Yeah.
Okay, let's move to that unsung hero in the middle, the wavy bit, the fluting medium. What's its crucial role?
The fluting medium. Its job is to give the board rigidity and cushioning. Think of it as the spring, the shock absorber inside the box structure.
The bouncy part.
Exactly. It's usually made from paper obtained from chemical pulp processes, again, often craft. Its main functions are providing that cushioning, giving rigidity, and helping the board resist bending, especially once it's folded into a box. It's really the engine of the box's structural integrity.
Okay, so structure and bounce. And the grammage, is it similar to the liners?
Generally a bit lighter, often in the 80 to 150 GSM range. And it's commonly made from straw paper, which is semi-chemical, maybe 25-75% straw pulp mixed with waste pulp.
Straw, like actual straw?
Yeah, plant fibers. Or it can be semi-chemical pulp, which uses a mix of chemical and mechanical treatments to get the right forming characteristics for those waves.
Fascinating. Okay, finally, the ultimate unsung hero holding this whole ingenious sandwich together. The adhesive. What kinds of glues are we talking about?
Right, the glue. Two main types here. First, you've got starch-based adhesive.
Okay.
This one's neutral, pH neutral. It dries a bit slower, which can be good. It's lighter weight and often used for the outer liner, especially if you need really good print quality.
And the other type.
That's sodium silicate-based adhesive. This is alkaline, it dries really fast, and it's heavier. It can make the board incredibly rigid.
Sounds good.
Well, yes and no. It can make it so rigid that it becomes brittle, and that can lead to delamination, especially in humid conditions.
So the box could just fall apart?
Potentially, yes. If it gets damp, not ideal.
Definitely not. So what makes for a good bond? What do manufacturers look for?
You want a good, solid content in the adhesive. That's the actual glue versus the water. Minimum around 16.5%, but ideally 20% or more. And you want about 5% adhesive content by the weight of the board itself.
And how do they check it?
Stringent quality control. They do things like the pin adhesion test, literally measuring how hard it is to pull the layers apart. They also look at the Cobb value of the paper.
Cobb value.
Yeah, that measures how much water the paper absorbs. If the paper absorbs too much water too quickly, it can mess with the glue's bond. Adhesive failure can happen from low solid content, poor application, or just bad quality glue or paper.
So it sounds like the type of corrugation, the flutes, that's the real secret sauce for strength and cushioning. It's not just the paper, but how it's shaped.
You've absolutely nailed it. The flute profile is critical. We use letters A, B, C, and E are the main standards, and each one offers a unique set of characteristics.
For today, we'll stop here. We encourage our students and viewers to take a moment to absorb the information we've shared. Stay tuned for the next part of the podcast. Until then, like, share, and subscribe to Packtra, your packaging partner.